Okay, let's get started. So good morning, welcome back. Happy Monday. Today is March 14. March 14 is a very special day mathematically. Today is Pi Day, 3/14, right? Andy, you said last year's Pi Day was even more special than this year's. How come?
This one's special if you round.
We don't round. How come last year was special?
Because
3.1415 are the next two digits, and last year was 2015, right? So now we're rounding, right? 3.14. No, I don't know. Okay, so all I'll say is this: celebrate responsibly later tonight. That's all. So today we are covering a little bit more on volume and then a brand new topic called arc length, and it starts here on page 43. So here we go. All right. Today we study another technique for finding volumes of revolution called the cylindrical shells method. In this technique, our slices are parallel rather than perpendicular to the axis of revolution. Okay, there's some cautionary language here, number one. We're just going to skip ahead to the example here. All I want to say, though, is that we're going to see a lot of formulas over the next couple of weeks, integrals that result from lots of different applications like volume and some physics stuff coming up next class. And I just want to highlight that even though at the end of the day you're going to just use one of these integral formulas, I don't want you to just kind of like sit around waiting for the integral formula of the day. I want you to understand why the slicing that we do is a natural way to solve these problems, and the integral is a consequence of the slicing that we're doing. All right, so don't just stick around for the formula of the day, but focus on why the integral is the right tool for all these different applications. Okay, we're going to take a look at number 3 here. It says, suppose the region between y equals x cubed minus x, that's this graph on the left, and the x-axis for 0 less than or equal to x less than or equal to 1 is rotated about the y-axis. So that's this region in the first picture. It's the shaded region, and we're spinning it around the y-axis. Now, last class, every slice that we drew was what? Parallel or perpendicular to the axis? It was perpendicular, and that's totally okay. Draw yourself a perpendicular slice. Well, don't draw that. But totally okay. And if you did that and you spun it around, what kind of a shape would you get from that one rectangle? We get a washer, yeah? That's groovy. So we know pi times the big radius squared minus pi times the little radius squared. So the big radius, well, even just the little radius, let's say the little radius is here to here, yeah? Take that guy and spin it around. Would you say that if I call this thing here x comma y, is that little radius a good name for that guy x or y? There's a good name for this distance, this green distance, x, or that's an x, right? That's what we mean by the x. But the thickness of this particular slice is a delta what? Is delta y. So for sure, we're not allowed to have x in our answer, right? We got to have only y's, only the letter after the delta, which means we need to solve this x cubed minus x equation up here for what letter? We need to solve it for x so that we can get rid of the x and have only y's, yeah? We need to solve that guy for x. Do you know how to solve that equation for x? I don't, but you guys might. I don't know how to solve that equation for x. What would you do? Yeah. I don't know how to solve that equation for x. It's a cubic equation. If it were a quadratic equation, I could solve quadratic equations all day, but cubic equations, I can hardly solve any of those. So solving for x is just, it's not something I can do. Now it turns out, just like the quadratic formula, there is a cubic formula. You'd imagine it would be quite a bit messier than the quadratic formula that you already know. So it is possible to solve that equation for x. I'm not saying it's not possible. All I'm saying is I personally don't know how to do it because I don't have the cubic formula memorized. That said, if I made it up here a 6th power, now it's impossible. There is no 6th power formula like the quadratic formula. So it's really easy to make equations that I can't solve for x. So since we can't solve for x, we're stuck. We cannot use the washer's method just because of this algebra difficulty. Okay. So if a horizontal slice didn't work for us, let's just try a vertical slice. Go ahead and draw this guy in. Now this is no longer discs and washers because as we saw, discs and washers require the slice to be perpendicular to the axis. So let's imagine taking that thing, I'll maybe draw a representative one over here where I've got 2 copies of my area drawn in. We're going to imagine taking that thing and spinning it around. Now you probably could call that guy a washer too, but we're going to give it a different name. What do you think? It's 2 cylinders, right? I mean, it's a big cylinder with mostly another cylinder empty. It's mostly empty. So we're going to call this a cylindrical shell. It's like the outer shell of a cylinder. Think of it as a soup can, no top or bottom, right? Soup can open on both sides. It has a tiny bit of thickness, just like a soup can does, but largely it is just the shell. Whereas when we say cylinder, we probably mean the whole thing filled in. So it will be filled in by other pictures like that, other cylindrical shells. It's going to be, this particular one is hollow, and in fact they're all hollow. Yeah, but what I imagine is taking a bunch of shells. So this paper has just a tiny bit of thickness. There's like a dx thickness there. And I can take it and wrap it around, and I get something very much empty on the inside, and it's a cylindrical shell, right? And it has hardly any volume, this thing, this piece of paper. There's volume inside, but that's empty. I'm not counting it. I'm just counting this piece of paper itself. But if you take lots of those guys, even though they're all thin and all hardly contribute anything, you would agree this is starting to get some real thickness, right? This stack of paper certainly has some volume. It's not as insignificant as it was when it was just one of them. So yes, it's going to end up being filled in, but this one is not filled in. None of them are filled in. At the top, I'm going to say there's no top or bottom to this thing. It is open all the way through. And the thing that's going to fill it in is going to be other of these pieces of paper of various heights. I'll show you another visualization here. Yeah, all right, let's come to this. Okay, imagine taking this shaded red region. We're going to spin it around this dotted line. So it's going to end up way over here, right? If I take that thing and I spin it around, I'm going to get one, like a soup can. This is going to be a fairly thick soup can. And so let's spin it. It's going behind the board first, and then coming out of the board at us, and then in front of the board. So that right there is one cylindrical shell, yes? Again, the thickness is way exaggerated just so that we can see the thing. But if you imagine taking that and having another one, we get this kind of like Colosseum type effect here. And if you add up the volumes of all of those cylindrical shells, you'll get an approximation for the actual solid itself. If you wanted a better approximation, more shells, right? Thinner shells and more of them. So Ben, are you with us? Each of these shells is empty, but there is a solid, which is the collection of all of these empty shells. Oh, I see. Gotcha. You were saying that we're not going to be able to see through this solid. I agree. There's just this one little point preventing us from seeing through. Yeah, but all I was saying is that the shell itself is empty. Okay. All right, so let's give this a shot. We need to know the surface area of that shell, of that piece of paper. Surface area. Okay, I don't know much about cylindrical shells, but I know that the circumference of the circle is 2 pi r. Yeah. And so then the surface area of one shell is 2 pi r times what? We'll get to the dx in a little bit, but times the height, right? That's the formula for the surface area of a shell. Just 2 pi r times the height. And so this calculus method that we're about to use boils down to that formula right there. We need 2 times pi times the radius times the height. Okay, so let's again label the point right here. It was x comma y before. I think that's a fine name for it. Just a generic point on the curve. What did we decide was a good letter to use for the radius, x or y? That's an x. And how about the height? That's a y. Easy. Yeah, one of them is the radius, the other is the height. And yeah, f of x is going to be our y. Okay, so let's see if we can find the volume of one slice. Here we go. So it's 2 pi RH, 2 pi. Instead of r, what letter? X. Instead of h, what letter? Y. But now we're going to give it a tiny bit of thickness. What's a good delta what for the thickness? That's a delta x here, right? The thickness of this guy right here is a slight change in x. What letter would I like to see only in this formula? Only x's because of the delta x, so that means y needs to change. 2 pi times x times, and then instead of y, x cubed minus x, right? That's what the y is. We're just changing it. We're given the equation, the relationship between x and y. I'm going to put there's a slight technicality here. If we just put x cubed minus x here, we're going to get a negative volume because all of those x cubed minus x's are negative y values. Yes? And so for me, the height, the radius, sorry, the red height is always a y at the top minus y at the bottom. What's the y at the top? How much is y at the top? It's always 0. And then minus how much is y at the bottom? Well, that piece is the changing x cubed minus x. So that's how I'm going to make that negative stuff turn into a positive when I throw it in my integral. Rob? Yeah, the top y, like if you imagine taking this blue cylindrical shell and just making it bigger and smaller, sweeping it all the way out, at the top of every one of these red line segments, the y value is 0 because the top is attached to the x-axis.
Oh, okay.
Yeah.
So
Well, in this one, the y is 0 at the top. Yep. Okay, and then I think I'm going to squeeze my delta x in there, and I'm feeling good about that expression. It's got only x's in it. We're happy. That right there would be the volume of one of those cylindrical shells, one piece of paper wrapped around. We're going to add up all the pieces of paper wrapped around. So imagine just throwing a sigma in front of that thing and then translating it into our integral. So the volume of the solid is yeah, so I'm just going to copy some stuff here. Let's see. So we've got x here times, and then 0 minus just becomes a negative x cubed plus x. Delta x changes to dx. From where to where? Negative 1 to 1 is a very common answer. 0 to 1 is another possibility. What do we think? Zero to 1 is going to take care of the other side of this picture. You let this red line segment run left and right through the shaded region, just the right-hand shaded region, but every one of these red line segments has one of these shells that flops all the way through the left-hand part. So we're not going negative 1 to 1. That would be double counting. 0 to 1 will take care of the whole thing. Okay, so that's it, and it's an easy enough thing to find an antiderivative of. Just distribute the x and then power rule. I didn't do this one already. I don't know what the answer is, and we're not going to spend our time finding it. It is what it is. Any questions on that? Yeah.
So could we possibly have an example where below the axis we have that negative step there?
I think that for me, it's always a y top minus y bottom, and I pay no attention to whether the region is above the x-axis or below. If you just do y top minus y bottom every time, you are forcing a positive thing, which is what a height should be. Yeah. Okay. So.
If it's x, it's an x right minus x left.
Yeah, if it's an x right minus an x left. It's always the big minus the small. That's the general thing. Okay, so here's our formula called cylindrical shells. The slice is parallel. That means it's quite different from what we did last class. 2 pi times x times f of x. And I'm thinking r times h, radius times height. Now that is a formula that will take you through a lot of problems, but honestly, it won't take you through all of them. You really do need to understand this radius times height business. Going back to the sketchpad thing, if we call the place where this red dot is here, this big X, like we're just calling that X, and we're spinning it around, looks like X equals -2 is the axis. What's the radius? Is it X? The radius of, yeah, what's the radius of that guy? It's X plus 2, right? It's not just X. X would only take you to the Y-axis, but this guy has 2 more that it has to go. So the radius is X plus 2, really X minus -2. And so inside of the integral, that one would have an X plus 2, not just an X. So that X times f of X formula, the integral, it's okay as long as you're spinning around exactly the Y-axis, but really better to just understand, have a good picture, and then understand, oh, I just need to calculate the radius. Chris? It would be the same? Would it be the same?
I mean, like, I know, like, for some, you know, for some of these,
Mhm. I think it's okay, but I think it would take a very special function to make it the same, right? I mean, like moving, if we move this guy over here, what happened to the volume of the solid? Did it get bigger or smaller or stay the same? Did that whole thing get bigger or smaller or stay the same? It got smaller because look, it used to be going farther away. Yeah, so provided you adjust the original equation, yeah, you could translate everything, and that's totally okay. But Chris, I don't think that was what you were saying. Yeah, so totally okay to translate, but I think that generally speaking, just moving this guy has a big impact on the volume of the shape. You'd replace the x with an x minus 2 right here. So it would just be 2 square root x minus 2. Yeah, totally fine. Okay. All right. So the other topic for today is a short one. It's something called arc length. Suppose we're still at the bottom of this page right here. Yeah, Chris. Mm-hmm. What page are you on right now? Yep. And then but you're not spinning it around the x-axis anymore, right? Let's talk. I'll walk around and we can talk about this one. But I think by changing this to an x, you also need to change the axis you're spinning around. But we'll talk about it. I'll come around. Yeah, Ben. Mm-hmm. Yeah. Yeah, that's right. That does not include the delta x, which gets plopped on at the end. Yeah. Okay. Yeah. Okay. So number 5 talks about the length of a curve. Just a quick drawing here. You guys know how to find the length. For example, suppose that I have the origin and I have the point 1, 1, and I wanted to find the length of the line segment connecting them. How would we do that? right? Pythagorean theorem is fine. You could also do the distance formula, right? Square root x1 minus x2 squared, right? Distance formula. Distance formula is great for finding the straight line distance, but that's all it finds, yes? So if I, for example, said, hey, well, I don't want the straight line distance. I want the distance along the parabola y equals x squared. It's about the square root of 2. Is it more or less? Yeah, square root of 2 is the straight line distance, right? So we know our answer is a little more than the square root of 2, but like at this point, we don't have any way to find the length of something that isn't just straight. Okay, so here's how you find the length of something that isn't straight. It's an integral. You're going to read the derivation of this as the first part of the activity, but for right now, we're just going to use it. But it turns out you just have to integrate from one point to another. So in this case, we'd go 0 to 1. Square root of 1 plus the square of the derivative of the function. So in our case, we'd take the derivative of x squared, plop it right in there. Yeah, it's not clear why that's the formula. Again, you'll read it in the beginning of the activity. But let's just use it real quick. Number 6. We're going to find the arc length of y equals cosine of x from 0 to 2 pi. I'll draw a picture, but really you don't need a picture at all for this guy. That's what we're after, right? It's the length of that curvy thing. So let's give it a shot. L equals integral from where to where? 0 to 2 pi is given. Okay, again, the formula is on the previous page. It was a square root of 1 plus the square of the derivative. So I'm just going to put something squared here. What's the derivative of the function? Yeah, the derivative of cosine. Oh yeah, the other one was the 2x one. So that's a negative sine of x. Yeah? Dx. So 0 to 2 pi, square root of 1, and then that just becomes all positive, right? 1 plus sine of x squared. Can we do this by hand? Yeah, it's not quite a trig identity, right? If it was 1 minus, we'd be in business, but it's 1 plus. Yeah, we actually can't do this one by hand. And in fact, the arc length formula is so complicated that there's hardly anything that we can do by hand coming out of that formula. So we're just going to type this in to the calculator and get our number. You can try a trig sub. I don't know what's going to happen, but you can try. All right, so what are we doing here? Math 9 square root 1 plus sine of x squared, parentheses, comma, x, comma, 0, comma, 2 pi. I typed that in right? I think that's all right. Okay, there you go. You guys are going to sleep better tonight knowing that the length of one period of the cosine function is about 7.64 units. Is that a reasonable number? If we had gotten 5, would that have been a reasonable number? What's wrong with 5? Yeah, right. I mean, we know for sure the curve is longer than the straight line, right? And the straight line is 2 pi. So we better get something bigger than 2 pi, which is about 6.28, but not a whole heck of a lot bigger. So 7.64 is in the realm of possibility. That's it. That's the arc length. Coming down here, any function. That's how you find arc length. And again, almost every single arc length calculation you're doing on the calculator once you've written the integral. Okay, I don't know how much experience we have with parametric stuff, but we're just going to throw a formula up here and use it. Don't sweat it if you don't have a lot of parametric experience, but if you have a parametric curve and you want to find the arc length, it's this formula. So for example, we want to find the arc length of this parametric curve. X equals 2 cosine of t and y equals 4 sine of t. So I'm going to say stuff. Again, it's okay if you don't follow all of this. X equals 2 cosine of t. So that's going to go over to left and right. And y equals 4 sine of t is going up 4 and down 4. And we know that sines and cosines just kind of wobble back and forth repeatedly. Anybody know the curve that I get if I, yeah. So we're hitting those 4 points, and it's going to be an ellipse in shape. I don't know which way it goes, but I'm just going to draw it, not put arrows. So we're going to find the arc length of an ellipse. We're going to find the length walking all the way around that thing. Okay. So, okay, if you didn't follow that, but let's see if we can plug into our new formula. L equals integral, where to where? 0 to 2 pi again, it's given. Square root of. So we're supposed to take the dx dt and square it. That is, take the derivative of x with respect to t. What's the derivative of 2 cosine t? Negative 2 sine t. And that gets squared, right? That's the derivative of x with respect to t. Plus derivative of 4 sine of t. 4 cosine t. And again, in the formula, that gets squared. dt at the end, and we're done. Again, I don't know how to integrate this thing by hand, so we would type it into the calculator just like it is. It actually turns out there's a simple formula for the circumference of an ellipse. That's not the right word. Circumference is a circle word. You guys know circumference of a circle is 2 pi r, right? Anybody know circumference of an ellipse? Yeah, I don't know it either. But there is a formula, and it will have pi's in it, which is appropriate today. So when I started that little anecdote, I actually thought that I knew the formula, and as I was talking, I was like, oh, I'm thinking of the area formula for an ellipse. So I do know that. The area of an ellipse is pi times a times b, where that's an a and that's a b. And so what's the area formula for a circle? Pi r squared. Do you buy that the circle formula is just a special case of our ellipse formula? Because for a circle, the a and the b are both what? They're both r, right? So pi times r times r. So you can forget the pi r squared formula if you know the pi a b formula.
So if that's the case, would that mean that the ellipse formula is just 2 pi r, but it's
Yeah, I don't know. As I said, in my head, I was scrambling. It's like, well, 2 pi r, what could it have come from? No, I don't know. We're gonna look it up in a second. You guys are gonna start reading the derivation of the arc length formula and then continue on the next page.